Well, this is John Black, super chemist. We're here. We're going to talk about wave particle duality, and we're going to talk about the double slit experiment. Okay, what is a wave? A wave is a stretched out and extended out into space, right? You can see this is a wave, right? And if you think about the ocean, you know, it's just, I mean, the ocean is basically just one big wave, a superposition of many waves, you know what I mean? But you can't really point at the ocean and say, there's the wave, there it is, because it extends, you know what I mean? It's not, a particle is a localized, you know, in space, not spread out. It's point-like, meaning that you can point to a point, and there it is, you know what I mean? I point to this ball, there's my particle, you know what I mean? But if I point to this wave, the wave is, you know, where is the wave? You know what I mean? Yeah, here's part of it, but so what is wave particle duality? Okay, that's the thing. The thing is that a particle acts like a wave and a wave acts like a particle. Okay, this is what they believe. Why does a giant particle not act like a wave? We never see a baseball acting like a wave, but small, you know, microparticles are like waves. They act like waves. And everyone is so confused, okay? It's like they can't add up 2 plus 2 and get 4. They always end up with 5 or 3 or something, right? Now, they admit, particles oscillate. They go up and down, up and down, up and down. The electron oscillates, okay? See this electron? Now, what happens when you oscillate and you move? Yeah, you create a wave. Yeah. So if a particle that's a ball like an electron, okay, not a spread out, you know, wave, right? If it oscillates up and down and moves, guess what? It creates a wave. Okay? The oscillation is a reaction, right, between space, right, permittivity, permeability, and the particles, you know, with charge and or magnetic dipole, right? The electron, the proton, they're both charged, right? And they have a magnetic dipole. The neutron has a magnetic dipole, okay? So these particles are definitely oscillating, okay? They're jumping up and down, up and down. I want you to pretend that these magnetic balls here are you know, electrons or whatever, some kind of particle that's really tiny, right? Look at that. Here, okay, well here, it's barely moving, right? But you give it more energy, right? Give it more energy, here it goes up and down. Give it more energy, it starts going back and forth. Give it more energy, it does both of them, back and forth and up. Then you do even more energy, now it just starts freaking out, like making kind of a U shape going back and forth. Small particles, they vibrate. And the more hot it is, the more they vibrate. But even at zero, absolute zero temperature, they still shake, they still vibrate. Okay? Imagine this guy right here, he's shaking, 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 he moves from here over to there. Yeah, he's going to make a little sine wave. Yeah, they're oscillating. Those are magnets. Just like electrons and protons and neutrons, all little magnets. Yeah, they weeble, they wobble, that they never fall apart, these atoms. Just in slow motion. It's wild as heck, Dad. You can see it, like transfer the energy, transfer it. Watch all. Look at it. Look at it. It's just like a wave. Look how it's a wave. See, when one jingles and jangles, the others jingle and jangle just from, you know, their fields touching each other. You know what I mean? Okay. But if you have a baseball, right, you're not going to see these tiny oscillations, right, within the baseball. It's not going to happen, all right? The baseball isn't going to go like this as you throw it, and it's going to be like a sine wave. No, no, no. Because the baseball in itself, it doesn't oscillate, okay? It doesn't have a charge, all right? It's neutral. It doesn't have a magnetic dipole. It doesn't have a charge. It's not going to oscillate, okay? Plus, it's giant, okay? For the space permittivity and all this stuff to oscillate something that giant, okay, come on. But the atom inside the baseball, right, the parts, right, the proton, you know, all these electrons, they are vibrating, up and down, right? Now I don't know if you can see that, but you can see there's different degrees of freedom for, you know, vibrations moving around. You can see that all different ways that these atoms are moving inside this molecule. You know, there you got your electromagnetic fields and stuff all interacting with each other. You have the 0 point energy. And, you know, overall, though, between all the atoms, you know what I mean, you can't see that vibration, you know what I mean? They're not all vibrating at the same exact time, you know what I mean? Some are vibrating this way, some this way, some this way, some this way, and they all kind of cancel each other out, kind of. So that you can't, you know, so the ball itself, the baseball made of these electrons and protons, actually, it isn't actually vibrating at all. I mean, it is. Everything actually vibrates slightly, you know what I mean? This camera, that board, everything, okay? But the thing that they get wrong, okay, right, up here, they say that electrons, or these, you know, small particles, they are neither a particle or a wave, okay? They are something else with characteristics of both. Okay, this is bull, all right? This is bull, okay? First of all, when you think of a, you know, an electron flying through the air, or, you know, light photons going through the air, when you're thinking about this wave-particle duality, okay, you should never, ever think of a wave, a water wave, okay? Because that's stupid, okay? Right? First of all, water waves, how are they made, right? You put your hand in the water and you go up and down, up and down. You oscillate, right? You oscillate, right? And the waves will be made by your hand oscillating. And you can just oscillate one time, right? If you get a pond, you throw a rock into the pond, right? That's just one oscillation. The rock goes into the water, goes down to the bottom, and it creates waves, right? But that's why you should never think of water is stupid, okay? This is what you need to think about. You need to think about this spring with this weight on it, right? You need to think about this orbiting thing, or this rotating thing, right? Or this pendulum that swings back and forth. These are the types of things that you need to think about when you are talking about wave-particle duality, okay? Because this is the way that it's talking about vibrating particles, okay? It's not talking about a water wave, all right? It's talking about a particle, a ball, right? A particle that moves up and down and vibrates relative to space-time, all right? Now, you might look at this and say, oh, this doesn't make any sense. Doesn't look like, you know, how does that look like a sine wave or whatever, you know what I mean? Yeah, you take the weight and you pull the weight down, right? Let go of the weight. It's on this spring, so it bounces back up and back and back. There's your oscillation. And you can see I drew a little sine wave. Obviously, this is in one plane, so that sine wave would just be a line. But so I drew it out this way, you know, so that you can actually see the sine wave. But if I pull it down to this bottom part here, I let go of it, it's going to swing up to this top, swing down, it's going to obey this sine wave, right? Same way with the rotating thing or the orbiting thing, right? It's going around and around and around. If I had my line here, every time this is going up, yeah, your sine wave goes up. And then it starts to come down, yeah, your sine wave comes down. And then as it goes this way, it goes up. Yeah, you're just creating a sine wave. I'm going to show you in here in a second, because me saying it and seeing it is two different things. Here's the pendulum, right? As it swings back and forth, it obeys this sine wave, right? And I know it doesn't seem like it does, but I'm going to show you some graphics, and then you can see that, yeah, it's exactly like a sine wave. Exactly. Look how it makes the pendulum. The pendulum, you know, floor's moving because the time moves, you know, but as it goes back and forth, it's creating a sine wave. See how it creates a sine wave? It's just a periodic, just like oscillation, you know what I mean? See, the floor is moving, right? Because time moves. So, but it shows that the pendulum is just going right on that sine wave as it goes back and forth. Now I don't know if you can see this as good as I can, but you can see this thing is oscillating up and down, up and down, up and down, right? I want you to notice the little green ball, if you can actually see it, okay? Notice how it goes in sync with that red box. The green thing, see how the green dot inside that red box, right, is keeping track. This orbiting thing is green too. It's a green dot. See how they're going together? They're in sync. You see how the ball is going up and down, up and down, up and down, just like this spring, right? Not in sync with it, but it's you can see how it does exactly. Now let's go to the board. Look at that. See how that blue ball in the middle, it's oscillating, right? Just like the spring. See how it follows that sine wave. Because it's, you know, as long as you are uniform velocity, you know, being orbited, or you're oscillating, these are all periodic, or the pendulum, these are all periodic things, right, that have a cycle. And when you're periodic like that, you're oscillating, you make a sine wave. I don't know if you can see that or not, but you can see the blue spring as it goes up and down. It's following the sine wave, the same way the black spring is following the black sine wave. That's all an oscillation is. It's just a periodic, that's what a sine wave is, a periodic thing that's happening. Now here's chlorine and hydrogen, right? Hydrogen chloride, an atom, I mean a molecule, right? Look how it's vibrating back and forth, back and forth, back and forth. Yeah, it's creating a sine wave there. That's what he's doing, right? I want you to check this out. See how this is rotating, right? I hope you can see this, but as the green, look, the green one is rotating, but this blue dot is going back and forth like an oscillation. But they're keeping in sync. You can see that they're on the x-axis at the same exact rate going back and forth, right? They both correspond to these sine waves. Do you see that? All oscillation and all rotation and all pendulums are the same thing as vibrating. Okay, you're just a sine wave. You're going back, you're up and down, you're just an oscillation. That's all you are. You can see here, you know, this is why they do that pi thing. 2 pi is one rotation, right? And so that means that they split this sine wave, right, both of them sine waves, up into 6.28 parts, because that's how many radiuses are in a circle. How does this relate to a circle? Well, we just saw. Here's another example here, okay? I want you to see, too, if, like, the red one is going up and down oscillating, right? It's in junction with this, right? Because this is the sine wave, right? And the sine wave is about the y-axis. That's why the red going up and down oscillating, right? Now the blue's going back and forth. I don't know if you can see it, but going back and forth on the x-axis, and he's in sync with this guy who's cosine. Okay, cosine just means that it's out of phase with this, you know what I mean? Instead of starting in the middle here, you start at the top, you know what I mean? So they'd be that much out of phase, right? But I want you to look at the black dot, if you can see it. It's the one, it's attached to the red dot and the blue dot, and it is going around, 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 around. That one correlates with both of these, right? Both of these sine waves, right? Because the black dot is moving through the x-axis and the y-axis, where the red one is only going in the y-axis, the blue one's only going in the x-axis. But you can see how rotation right? Or oscillation is the same thing pretty much when it comes to a sine wave, right? You're going to create a